with our Winter 21 question paper 4.2, question 12. Okay, we're getting through this quite nice and quick. Okay, as usual, the starter of this question, nice and easy. We just want to remember a number, okay? And that is the speed of light in a vacuum. You will never be asked any other speed of light in any other material, just simply in the vacuum, okay? 3 times 10 to the 8, or if you would like to write it in longhand, 300 million meters per second, okay? You can see really here why scientific, or I suppose more mathematical notation is important. Okay, we've got 3 times 10 to the 8 meters per second. All right? We're then going to use that value, okay, to calculate the frequency of red light. We're told the wavelength, and we're going to link the two. Now, V equals F lambda may be an equation you know already. I like to encourage people to use mnemonics. So very fast waves, quite like that one actually, quite happy with that. Very fast wave, V F W lambda, okay, is the way that I would remember it. V equal to F lambda. Well, if we know V is 3 times 10 to the 8, and lambda is 7.1 times 10 to the minus 7, then we're going to do a bit of dividing, and we're going to get 4.23 times 10 to the 14, a stupidly large number, all right? But not a surprising one. We expect those kind of values when we are doing these questions, folks. Don't be surprised if your frequencies are large. 10 to the 14, completely standard, okay, for the frequency of visible light, certainly. Other frequencies will change. Okay, let's see if we can pump through this, all right. We're gonna look at a laser which emits a ray of light, and we can see it passing through. Now, this is the change of direction of light as it passes from one medium to another. In this case, we're passing from air into glass and then back into air again, okay? And this is refraction. Again, all you're saying is that you know that this is refraction. It's not reflection, not diffraction, it's refraction. Making sure I can say that, it's quite difficult to say it quickly. We've got a couple of marks later to describe what causes this, okay? Well, the point being here is that when you go, when you do refraction, you change your direction, and that direction change is to do with the fact that the speed is different in each of these materials, okay? And you can imagine this, I mean, we do use often an analogy, for example, where we have, if you were to walk, and then one of your legs were to become slower than the other ones, you would change your direction. That's exactly what's happening with light. When light enters, say, glass, it slows down, and part of it slows down first, which then causes a change in the direction. What you need to have is the fact that light is changing its speed as it crosses from between the two materials. And I'll be honest with you, I probably wouldn't trust myself to remember that point later. Okay, really, the key idea here being change of speed, okay, and the different materials, okay, different materials being key idea there. So we change materials. Obviously, if you passed from air to air or water to water, then there would be no refraction because there's no change in speed and therefore no two different materials there. All right, we're pretty much done for this question. I'm quite impressed at how quickly this has gone. All right, nice little efficiency calculation to finish this off. We're told we've got a useful power output of 1,200 watts, I should say, and 80% efficient. And we're asked to calculate the input power of the laser. Now, let's think about this just very carefully. We know that efficiency means that energy is wasted. So here we're expecting 20% of my energy to be wasted. What that means is that the power in must be bigger than the power out. Okay, so anything you calculate here is going to have to be bigger than the original value here. So we've got 1,200 watts. Where did that 1,200 come from? Well, if we then do the maths, the efficiency is the ratios of powers out, useful out, I should say, over power in. We've got 80% or 0.8 is 1,200 divided by that power in value. We're going to rearrange it, and therefore we've got 1,200 divided by 0.8. Now I know, one thing I know about maths is that if you divide a number by something less than 1, you're going to get a bigger number, and that's 1,500, and that looks about right for our efficiency. Sorry, for our power in, all right? So you put in 1,500, and you've got 1,200 out. In other words, you're wasting 300 watts, okay? I find that one okay. Actually, I think that was quite a nice little mixture of different things, some bits of waves, some bits of energy, etc., etc. Folks, usual story. If you've got any questions, you'd like more videos, ask me. I'm more than happy to help. Thank you for watching.